Hello, my name is Victor, and this presentation summarizes our study on Python performances with and without NumPy. The objective of this project was to compare the execution speed of pure Python implementations against NumPy implementations for two fundamental operations. Element-wise vector multiplication and true matrix multiplication. Performance was measured using median runtimes across multiple trials for increasing input sizes ranging from small vectors to 500 by 500 matrices. All experiments were conducted using float64 data types and controlled random initialization to ensure reproducibility. The results show that while performance differences for small inputs were moderate, the gap increases significantly as problem size grows for large matrix multiplications. NumPy achieved compared to pure Python libs. This study highlights the scalability limitations of interpreted loops-based computation and demonstrates the importance of vectorized compiled and numerical libraries in scientific and engineering applications.
Now, the theoretical background. Matrix multiplication has a computational complexity of n of n cubed. This means that as a matrix dimension increase, the number of required operations grow very rapidly. When implemented using triple nested loops, execution time scales directly with this cubic growth. In pure Python, performance is further affected by interpreter overhead. Each arithmetic operation requires runtime type checking and object handling. Python lists also store reference rather than continuous numeric values, leading to inefficient memory access and reduced cache performance. NumPy improved performance by using continuous memory arrays with fixed data types like float64. Most importantly, it delegates computation to optimize compiled BLAST libraries, which leverage sync instructions, cache optimization, and parallelism. This architecture difference explains why NumPy achieves significantly better scalability for large matrix operations.
Now results. Vector multiplication showed a linear growth with NumPy being faster than pure Python, though that increase at the start was small with only 1.2 times faster, but then increased to 3.4, 5.8, and then to 11.5 until it was 500, where it was 24 times faster than pure Python. For matrix multiplication, the pure Python runtime grew dramatically, where in 200 elements it took a few seconds for it to run, but in 500 elements it took multiple minutes for it to finally register the result. And throughout the time, NumPy maintained a low execution time. It was never higher than 0.004 seconds. Meanwhile, pure Python at the 500 elements took 18 seconds for it to run. And the speed up, since the start was also in favor of NumPy, even more dramatically, with the lowest being 38 times faster, and the highest at 500 elements for 4,303.
In comparison, the main difference comes from how each implementation executes the operations. In pure Python, matrix multiplication is done using nested loops, and every single arithmetic operation is processed by the interpreter. That means there is runtime type checking, object handling, and repeated memory access for each element. As the input size increases, this loop-based execution adds a very high overhead, which causes the rapid growth in execution time. NumPy works in a completely different way. Instead of executing element by element in Python, the operations are delegated to compiled code. The data is stored in contiguous memory with fixed data types, which improves cache efficiency and reduces the cost of accessing elements. Because the heavy computation runs in optimized BLAS backends at machine level, the interpreter is no longer the bottleneck. In conclusion, this is why pure Python does not scale well for large numerical problems. While NumPy achieves scalable performance, the vectorized and compiled execution allows it to handle large datasets efficiently, making it the preferred option for scientific computing, data processing, and machine learning.